Every smooth train ride hides a secret. It isn't just the locomotives that keep railways alive, it's the machines that maintain the tracks, working quietly, brutally, and without recognition. Some of those machines were built over half a century ago. No computers, no sensors, just steel, hydraulics, and engineering meant to survive endless vibration, weather, and abuse. Against rust, against time, and against replacement, they're still out there grinding rails, lifting tracks, packing ballast, and keeping trains moving safely. Today, we're counting down the 10 old railway maintenance machines still working after 50 years. The forgotten giants that refuse to retire and prove that real engineering never dies. Get ready, because these machines have outlasted generations of trains. Number 1. Track tamper. Mechanical tamping machines. Mechanical track tampers are among the most enduring railway maintenance machines ever built, and their survival after more than 50 years is no accident. Early tampers from the 1960s and 1970s were designed at a time when railways demanded absolute reliability in remote areas with minimal support infrastructure. These machines were engineered with massive steel frames, oversized hydraulic cylinders, and mechanical linkages that prioritize strength over efficiency. The core purpose of a track tamper is simple but critical: compacting ballast beneath railway sleepers so that the track remains stable, level, and aligned under heavy train loads. While modern tampers rely heavily on computerized geometry correction systems, older mechanical tampers achieved impressive accuracy through physical guides, operator skill, and raw hydraulic force. What makes these old tampers still viable today is their repairability. Every major component, tamping tines, vibration units, hydraulic pumps, and rams, was built to be removed, rebuilt, and reused. Railway workshops routinely remachine worn tines, replace seals, and fabricate bushings locally, extending the machine's service life indefinitely. Unlike modern tampers that can be rendered useless by a failed sensor or software fault, a mechanical tamper can often be repaired trackside with basic tools. Another key factor is duty cycle. Tampers do not operate continuously year-round. They are deployed during maintenance windows, used intensively, and then stored, which greatly reduces long-term wear. Many of these machines have been quietly modernized without altering their core design. Upgrades such as improved hydraulic hoses, modern diesel engines, and basic electronic safety interlocks allow them to meet today's operational standards while preserving their original robustness. On secondary lines, industrial sidings, and rural rail networks, these tampers remain indispensable. Their continued operation proves that when a machine is designed for strength, simplicity, and maintainability, it can remain productive for generations. Number 2. Ballast regulator. Ballast sweeper. Ballast regulators built more than 5 decades ago are still shaping railway trackbeds today, and their longevity highlights the brilliance of straightforward mechanical engineering. These machines are responsible for redistributing ballast after tamping, shaping the track shoulders, clearing excess stone from sleepers, and ensuring proper drainage along the rail corridor. Older ballast regulators were built on heavy rail-mounted or road rail platforms with thick steel blades, reinforced frames, and uncomplicated hydraulic systems. At the time, manufacturers expected these machines to operate in harsh environments filled with abrasive stone dust, moisture, and constant vibration, so durability was prioritized above all else. The working principle of a ballast regulator has changed very little over time. Adjustable plow blades push ballast into position, while rotating brushes or sweepers clean the track surface. Because this work involves slow, controlled movements rather than high-speed precision, older machines remain perfectly suited for the task. Their hydraulic systems are easy to service, and worn cutting edges can be replaced or resurfaced in local workshops. Even severe frame damage can often be repaired through welding, something that would be unacceptable or impractical on modern lightweight designs. Another reason these old machines persist is their versatility. A single regulator can be fitted with different blade configurations to handle shoulder shaping, ditch cleaning, or ballast profiling. This adaptability allows railways with limited budgets to accomplish multiple maintenance tasks using one machine. Over the years, many regulators have received safety upgrades such as better lighting, enclosed operator cabins, and improved braking systems, but the core machinery remains original. On branch lines and freight corridors, These machines continue to deliver consistent results with minimal operating costs, proving that heavy steel and simple hydraulics still outperform complexity when longevity matters. Number 3. Rail grinder. Early rail profiling machines. Early rail grinding machines represent one of the clearest examples of how function-driven engineering can outlast technological trends. Rail grinders built in the 1960s and 1970s were designed to correct rail surface defects such as corrugation, spalling, and uneven wear, problems that directly affect ride quality, noise levels, and rail lifespan. These early machines used mechanically mounted grinding wheels driven by electric motors or belt-driven systems, all housed in rigid steel frames capable of withstanding constant vibration and heat. The reason these machines are still operating after 50 years lies in the simplicity of the grinding process itself. Grinding is inherently mechanical. Abrasive wheels remove metal from the railhead to restore the correct profile. As long as the grinder can maintain consistent pressure, speed, and alignment, it can do its job effectively. Older grinders achieve this through adjustable mechanical mounts and operator-controlled settings rather than automated software. This makes them easier to maintain and far more tolerant of wear and imperfect conditions. Railway maintenance crews have kept these machines alive through regular refurbishment. Bearings are replaced, motor windings rewound, and grinding heads rebuilt using modern abrasive materials that actually improve performance beyond original specifications. Some older grinders have even been retrofitted with modern dust suppression systems to meet environmental regulations. On lightly trafficked lines, heritage railways, and regional networks, these machines remain an economical solution for rail maintenance. Their continued use demonstrates that when a machine is built around a fundamental physical task rather than complex electronics, its relevance can span generations. Number 4. Track geometry. Car, mechanical, and optical measurement units. Track geometry cars from the mid-20th century may look primitive compared to today's sensor-packed inspection trains, but many are still in active service because of their remarkable accuracy and resilience. Early geometry cars relied on mechanical linkages, optical measurement systems, and precision gauges to measure critical track parameters such as gauge width, alignment, cross-level, and vertical profile. These systems were designed to provide direct physical measurements rather than interpreted digital data, giving engineers immediate and trustworthy results. The durability of these cars stems from their construction philosophy. Frames were rigid, measuring arms were overbuilt, and optical systems were protected within sealed housings. Unlike modern electronic sensors, mechanical and optical components are not vulnerable to electromagnetic interference, software glitches, or data corruption. When something wears out, it can usually be repaired or recalibrated rather than replaced entirely. Railway workshops routinely refurbish these units by replacing bearings, realigning optics, and restoring worn measurement arms. Another reason these geometry cars persist is human expertise. Track inspectors trained on these systems develop an intuitive understanding of track behavior, allowing them to interpret readings in context rather than relying solely on automated alerts. Some operators have enhanced older cars by adding digital data loggers or GPS tracking, combining modern record-keeping with proven measurement methods. On secondary routes and regional networks, these cars remain cost-effective, reliable tools for ensuring track safety. Their continued use proves that accuracy does not always require complexity, and that well-designed mechanical systems can remain relevant long after newer technologies emerge. Number 5. Spike driver and spike puller machines. Spike driver and spike puller machines are some of the most brutally simple yet long-lasting railway maintenance tools ever created. Built primarily in the 1950s, 60s, and 70s, these machines were designed to handle one of the most physically demanding tasks in rail maintenance: installing and removing steel spikes that secure rails to wooden sleepers. Early mechanized spike drivers relied on heavy pneumatic or hydraulic ramming systems mounted on rail trolleys or small self-propelled platforms. Their construction was unapologetically heavy, with thick steel housings, oversized pistons, and impact mechanisms designed to withstand millions of repeated strikes. What makes these machines still functional after 50 years is their mechanical honesty. There are no sensors, no computer logic, and no delicate electronics to fail. The working principle is direct. Energy is transferred from the ram to the spike, driving it into timber, Wear parts such as striker heads, seals, and chisels are easily replaceable, and many railway workshops fabricate replacements themselves. Because these machines operate intermittently rather than continuously, fatigue damage accumulates slowly, allowing decades of service life. Another key reason for their survival is compatibility with legacy infrastructure. Many railway networks still use timber sleepers on secondary routes, sidings, and yards. Modern fastening machines optimized for concrete sleepers are often unsuitable in these areas, making older spike machines not just useful but necessary. Operators also value the tactile feedback these machines provide. Experienced crews can sense when a spike is correctly seated, reducing damage to sleepers. With minor safety upgrades such as improved guarding and emergency shutoffs, these old spike machines remain reliable, cost-effective tools that continue to perform essential work without interruption. Number 6. Rail-mounted cranes and wrecking cranes. Rail-mounted cranes, often referred to as wrecking cranes, are among the most visually iconic and structurally durable railway maintenance machines still in service today. Many of these cranes were built between the 1940s and 1970s, originally intended for derailment recovery, heavy track component installation, and bridge maintenance. Their survival for over half a century is rooted in conservative engineering practices that emphasized extreme safety margins. Thick lattice booms, massive counterweights, and low-stress load paths were standard, allowing these cranes to endure loads far below their structural limits during normal operations. Unlike modern cranes that rely heavily on electronic load monitoring systems, older rail cranes depend on mechanical gearing, winch drums, and manual or semi-hydraulic controls. This simplicity makes them easier to maintain and far more tolerant of harsh operating conditions. Maintenance crews regularly replace wire ropes, refurbish bearings, and rebuild hoist mechanisms using conventional workshop tools. Many older cranes have undergone diesel engine conversions, replacing obsolete power systems while retaining the original lifting structure. Another reason these cranes remain in service is their operational role. Wrecking cranes are not used daily. They spend much of their lives stationed strategically across a network, ready to respond to emergencies. This low utilization dramatically reduces wear, enabling them to remain structurally sound for decades. In derailment situations, crews often trust these familiar machines more than newer alternatives, especially in remote areas. Their continued use reflects a railway culture that values reliability, operator familiarity, and proven performance over technological novelty. Number 7. Ballast cleaning and track renewal machines. Early ballast cleaning and track renewal machines represent a class of equipment designed to solve fundamental infrastructure problems rather than chase efficiency metrics. Built primarily in the 1960s and 1970s, these machines were tasked with removing contaminated ballast, separating reusable stone, and restoring proper drainage beneath railway tracks. Their designs relied on mechanical screens, vibrating conveyors, and plow systems powered by robust diesel engines and simple hydraulic circuits. These systems were intentionally modular, allowing worn components to be replaced without dismantling the entire machine. The longevity of these machines lies in their tolerance for abuse. Ballast cleaning is an inherently abrasive process involving stone, dust, moisture, and constant vibration. Early designers compensated by using oversized bearings, reinforced frames, and slow-speed conveyors that minimized stress. When components eventually wear out, railway workshops can fabricate replacement parts locally. Modern renewal machines may offer higher throughput, but they also require specialized diagnostics and factory support, making older machines attractive for smaller railways and regional networks. In practice, these vintage machines are often used in combination with manual labor and modern surveying tools. The machine handles bulk material separation, while crews fine-tune the trackbed afterward. This hybrid approach extends the usefulness of older equipment and keeps capital costs low. Because ballast renewal cycles are infrequent on low traffic lines, these machines may only operate periodically, further extending their service life. Their continued operation demonstrates that rugged mechanical solutions remain effective long after their original production era. Number 8. Hydraulic track jacks and manual maintenance tools. Among the oldest railway maintenance machines still in daily use are hydraulic track jacks and manual track tools, many of which have been in service for over 50 years. Hydraulic jacks, developed in the mid-20th century, were designed to lift rails and sleepers during alignment and replacement work. Built with thick-walled steel cylinders, simple piston designs, and mechanical locking systems, these jacks were engineered for safety and durability rather than convenience. Their failure modes are obvious and gradual, making them ideal for field use. Manual tools such as lining bars, tamping bars, and rail levers are even older, often passed down through generations of track workers. These tools are nearly indestructible, with wear limited to bending or surface deformation that can be corrected through forging or welding. The reason these tools endure is straightforward. They require no external power, function in any environment, and can be repaired or replaced locally. Despite advances in mechanized maintenance, these tools remain indispensable. In tight spaces, emergency repairs, and remote locations, manual and hydraulic tools are often faster and more reliable than deploying heavy machinery. Railway crews trust them because they are familiar, predictable, and resilient. Their continued use highlights a fundamental truth of railway maintenance. No matter how advanced technology becomes, simple, well-made tools will always have a place on the tracks. Number 9. Ballast hopper wagons and mechanical distribution systems. Ballast hopper wagons are some of the most overlooked yet longest-serving railway maintenance machines still operating today. Many of these wagons were built in the 1960s and 1970s, designed to transport and precisely distribute crushed stone ballast along railway tracks. Their durability comes from an extremely simple but effective design philosophy: heavy steel bodies, sloped hopper interiors, and mechanically actuated discharge gates. Unlike modern ballast distribution trains that rely on electronically controlled conveyors and sensors, older hopper wagons use gravity and mechanical linkages to do the job, which dramatically reduces the number of failure points. The longevity of these wagons is largely due to their low mechanical complexity. The most critical components, gate hinges, locking arms, and control rods, are easy to inspect and repair. When wear occurs, railway workshops can rebush pivot points, remachine gate surfaces, and weld reinforcement plates without specialized equipment. Since these wagons operate at low speeds during maintenance work, structural stress is minimal compared to high-speed rolling stock. Their underframes and bogies are built to freight standards, allowing them to endure decades of service with routine wheelset and bearing replacements. Another reason ballast hopper wagons remain in use is operational flexibility. They can be mixed into standard maintenance trains, used on remote lines, and operated manually when automation is unnecessary or unavailable. Many railways have upgraded these wagons with modern braking systems, reflective markings, and improved control mechanisms while retaining the original hopper structure. Their continued presence on rail networks worldwide proves that when a machine's task relies on basic physics rather than electronics, its service life can easily exceed half a century. Number 10. Thermite welding equipment and early rail repair units. Thermite welding equipment represents one of the clearest examples of railway technology that has remained fundamentally unchanged for over 100 years. Many thermite welding rigs and mobile rail repair units currently in service were built more than 50 years ago, yet they remain indispensable for emergency rail repairs and track maintenance. The reason for this longevity lies in the nature of the process itself. Thermite welding relies on a controlled chemical reaction rather than mechanical complexity, producing molten steel that bonds rail sections together with remarkable strength. Older thermite welding setups typically consist of steel frames, crucibles, molds, and preheating equipment mounted on rail trolleys or small trailers. These components were designed to withstand extreme heat, rough handling, and outdoor conditions. Wear items such as molds and liners are consumables by design, meaning the core equipment rarely needs replacement. Maintenance involves cleaning, inspection, and occasional fabrication of replacement parts, all of which can be performed in railway workshops. Mobile welding trailers and early electric arc welding units follow the same pattern of longevity. Heavy transformers, simple control panels, and rugged cable systems make them reliable even in adverse conditions. Over time, railways have modernized safety gear and personal protective equipment while keeping the original welding platforms intact. Experienced welding crews value these older systems because they are predictable and field repairable, especially during time-critical situations like broken rails. The continued use of these machines highlights a key principle of railway maintenance. When human skill and robust equipment work together, technological age becomes irrelevant. These welding systems remain trusted tools, proving that durability and simplicity can outlast generations of newer alternatives. Those were the silent heroes of the railway world. Machines built to work in the shadows, endure decades of punishment, and never fail when safety is on the line. While modern equipment comes and goes, these old maintenance legends are still earning their keep, one track at a time. Which of these railway machines amazed you the most? Tell me in the comments. I read every one. If you respect old-school engineering and unstoppable machines, hit like, subscribe, and share this video with a fellow railway enthusiast. Thanks for watching, and until next time, keep the tracks smooth and the legends running.